I'm here for my weekly heart to heart, one of my favorite parts of my week, and one of my favorite guests, Dr. Stephen Edwards from Columbia University, a computer scientist. How are you today, Stephen?
Doing pretty well, although it's a wee bit warm outside. My outdoor thermometer's reading 121, but I don't believe it.
Wow.
Yeah.
Um, I want to do a few housekeeping things for those of you new. I run a company called RoboFun where we help children love to learn by making, creating in digital platforms. So right now, as we speak, we have a number of kids at our office in summer camp. Right now they're eating lunch, but all morning they were building robots, and all afternoon they will be programming or doing circuitry projects within Minecraft and actually within physical making of the projects. So we offer programs for 3 to 13-year-olds at 102nd and Broadway. And we are finishing, I believe this is our 7th out of 12 weeks of summer camp. And summer camp is going really well. So if you're looking for something for your children, please look us up at robofun.org. If you like what you're hearing, you like our Instagram feed, you like what you're hearing with Stephen and I, please click the likes or the hearts or whatever the platform tells you to do. It really helps let other people know about us. We're a little niche business that does creative things with kids in a with very high standards. Our goal is that our kids go home having had a great time learning and making friends and really enjoying themselves. Because we believe that if you're really loving what you're doing, you're learning a heck of a lot. So robofun.org. And we also do birthday parties, private lessons, bring your child to work days. We can work with your corporation, whomever you work with. So that's my little pitch for the company. And once a week, I invite a guest to join me and to talk about some aspect of learning, technology, education, things that apply beyond the classroom. And actually, that is somewhat of our topic today is coding and learning and life. I liked the L's and L's there. And the idea is something I talk a lot about, and I think Stephen and I think about a lot is this just an experience where you're on a screen making things happen, or does it apply to the rest of your life in other aspects of academia, but other aspects of just basic daily life? So I'm going to turn that big, huge question over to Stephen. You can take chunks of it. Stephen's children have been RoboFun kids with us. His older one was an intern for a while, and Stephen teaches graduate. Primarily, why don't we just start? What exactly do you do at Columbia, and then we can jump into this topic.
What do I do? Well, I'm a tenured faculty member, so that means I spend half of my time teaching, half of my time doing research, and half of my time raising money for doing research.
Yep.
But broadly, I teach upper division undergraduates in computer science. I had been teaching a compilers class. Mm-hmm. So if you've ever written a Java program, you run that through a compiler to get the computer to do it. Or with Python, not quite, but yeah, it's a similar sort of thing. Mm-hmm. We also do an embedded systems class, which is sort of, think of it as, bits of RoboFun, but, after another 15, 20 years of education, this is the point we get. We build things like 80s era video games where I have the students design the video creation stuff, which is an interesting challenge because there's not quite enough memory on the board, which is a good thing. But it's great fun, and I love tinkering. This is what I have on my desk in front of me here. This is actually a research project. So this over here, it's funny. This has close to the same chip as the BBC microbit, which we were talking about just earlier, except it's a more professional development board and so forth. Anyway, I'm writing software that goes onto this board, onto this chip here, and then this little thing is actually a frequency counter that tells me whether the software is doing what I expect. And this is the kind of stuff I love. And to echo what you were saying earlier, one of my central thoughts and challenges in life and in teaching and so forth is you only learn it if you love it. You can sort of force people to try to do this and make sure that it's on the test, and oh, you got to figure this stuff out, and basically it's the stick approach of saying, oh well, if you don't learn this, you're going to be in trouble. But the carrot works so much better.
Yep.
If you can do it, but it's a much harder thing to engineer.
It's interesting because it's harder to engineer, but once you do the flip, it's the difference between, in a RoboFun class, we have between 6 and 12 different things going on at once. It's like having a cook with 12 burners going, and the teacher is really busy going from project to project to project, and it's not the same exact thing from child to child. So the teacher is really busy. The kids are really happy. The other way of doing it is you have one thing going on and everyone's doing it, and half the kids are like, yeah, okay, And how to make that change puts a lot more pressure in many ways on the teacher, yet it's much more fun as a teacher.
Yep. Yeah, it can be. That one of the big challenges is scalability in situations like that, right? We're at Columbia, like virtually all computer science higher ed in the US and across the world, we have far too many students and far too few people to teach them, and so we have these enormous, and to have the luxury of only having 6 things going on or 6 groups of things going on in a classroom is enviable. I love that. That's incredible. You can't do that when you're lecturing to 200.
Yeah.
And it's a challenge. So yeah, the trick is in situations like that to give students enough flexibility in what they need to do that maybe they can find their own passion and interesting things and so forth. But I'm a big believer in trying to do that. I don't quite know how to always do that, but it's always, well, I find that kind of interesting. With luck, maybe my students would too.
Right. So if we switch to the idea that, it slightly relates to the thing that everyone says in math class, like, why are we bothering? Why are we doing this? How do we, but let's hold that, put that aside for a minute. But, and let's talk about the idea that if you learn how to, what used to be called programming, and now the cool phrase is coding, how does that relate to other areas of learning? And how does that relate to other areas of life? And how do you think about that?
Yeah. So the joke is I got into engineering and so forth, so I wouldn't have to deal with people. And it obviously hasn't worked out very well. But it's a different kind of world, and it's a different kind of challenges, right? Computers generally don't learn, modern AI stuff notwithstanding. They're very, very obedient. They do exactly what you say. If you say something wrong, they do something wrong. If you say something right, they do something right. They do it the same way each time.
So wait, before we go on, let's just break that down. If you say something wrong for the average layperson, or if you do something wrong, what are you saying? That the lines of your code are not correctly written?
Well, if you ask it to do nonsense, it will do nonsense.
Okay.
Right. It has no common sense. It has no idioms or anything like that. Right. One of my jokes is to be a good computer scientist, you need to be a smartass. So a smartass, and
I don't think you have to worry about that, Steve.
I've got it covered. The slightly more serious point I make with this is that, being a smartass is doing things like pointing out the obvious or misinterpreting things in a way that is literally correct but idiomatically wrong. Stuff like this. Smartass is me saying, "Oh, all of my blonde girlfriends were 6 feet tall," which is a true statement, but it's a smart alecky statement because, of course, that's an empty set. And so it turns out I like brunettes, whatever. But it's that kind of thinking that you have to be constantly worrying about if you're dealing with computers and, to a slightly different extent, electronic devices and so forth, but certainly digital devices. I like to joke, this is the one place where, George Bush foreign policy, it's all binary, right? It's 1 or 0, and that's all it is. It's a remarkably powerful, successful way to do things in the world. And the fact that every single one of us has a supercomputer in our pocket masquerading as an iPhone or something like that is testament to that. But it's a very different world. It's a very different way of doing things than normal human interaction stuff. And that appeals to people such as myself. It is anathema to many other people. And there are, everybody in between needs to straddle both worlds somehow. And
so then how is that, so how does that help a 10-year-old who's just registered for our Python class? How does learning this other way help him in other areas of learning or other areas of life, to put you right on the spot?
Right. Well, there's two things. There's the very cynical, computers are everywhere, so you better learn how to use them.
I reject that.
Very straightforward. Yeah, no, it's kind of, tail wagging the dog kind of a thing.
Right.
The next thing is to understand that many of the issues you have in teaching a computer how to do things and controlling it and figuring out whether it did the right thing and so forth actually starts to extend into different parts of life and understanding what can and can't be done and so forth. Let's see.
Here's how I think about it, and I'm at a really different level than you are, but is that to write a really effective program, you have to break things down to all the little steps. When I was taught programming to begin with, there's this exercise of how do you tell somebody how to make a peanut butter and jelly sandwich, and
right.
The detail of take the bread, take a knife, and every single step. And what that helps me understand in the rest of my life is that there are a lot of other complicated situations that I have to break down into every step, and that kids have to break down into every step. How do you get yourself to school on time? And for especially in my life, I'm familiar with a lot of kids with ADHD, and they're brilliant in many ways, but the actual getting to school with teeth brushed, with shoes on the right foot, with your backpack actually with the homework in it, having had breakfast before, et cetera, is sort of similar to writing a computer program.
Yep. Now, it raises an interesting question of, is that the right way to control human beings, thinking in that way? But certainly that's a big chunk of it. I'll share a wonderful vignette. Another professor friend of mine has a daughter who's currently attending Columbia, in fact. When she was, 10 or probably even younger than that, was having exactly the, how do you get out the door to get to school in the morning problem. And the solution her mother came up with was it was kind of like a book, but the pages were rigid, bound to the wall. And it was just a series of what you had to do in order. Right. And, the first one was get out of bed. So you would then turn that over. I'm not doing this quite right. And then the next one would say, go to the bathroom. And the next one would say, remove pajamas. Next one would say, put on clothes and so forth. And then what was really funny is the very last one was reset the book for tomorrow morning.
Right.
Very much a programming way of looking at it. I think what you're describing, however, is actually a marvelous segue into sort of, what has computer science done for the world? What is its biggest contribution?
That's
and
great.
You can argue that, okay, maybe this is a mathematical notion as much as anything, but I think what you just described is abstraction. And it is exactly the how do you turn a high level command like get to school on time into a series of tasks that you do? Make a peanut butter and jelly sandwich. I because of the things that I'm thinking about, and in fact is relevant to our robot thing. What is the information that you need? Well, it's actually a series of pulses that you need to tell the stepper motors to rotate, to move the hand, to grab the thing, and all the rest of it. This is incredibly low level stuff, and it isn't even the lowest level stuff. But
what do you mean when you say low level?
So level of detail, I guess.
Okay.
So high level is make a peanut butter and jelly sandwich. Slightly lower level is get the peanut butter out of the cupboard, get the jelly out of the refrigerator, things like that.
Mm-hmm.
Much lower level is, pick up a knife, rotate to this degree. And even lower would be something like if you actually had a physical robot going with that. Somewhere there's something saying, okay, make this little electric pulse that moves the arm just a little bit more so that you can get the thing into the right position and so forth.
So it's the really very discrete little units that get built together.
Yeah, and broadly it might be the number of them. Certainly it is the complexity of them and what it takes to sort of execute the stuff underneath. I understand you're in the middle of a horrendous renovation project involving New York real estate and so forth, right? The high level instruction is very simple. It's make this space acceptable for my use, and the low level is at some point is going to be swing this hammer. Kind of a thing, but there's all this junk in between. And to a large extent, a lot of what we do as professionals, as workers, as whatever, is take high-level instructions from wherever and turn them into the low-level operations that need to be done. And this is exactly what you need to do to program a computer, and exactly what you need to think of if you want to develop better computer using models and so forth. And how do you deliver that to users, to kids, to students, things like that.
Right. Okay. So it's an interesting thing to think about. I'm relating it to an experience I had this week where the whole world uses Google Sheets, Google Docs, Google, and all of a sudden I'm using Google Sheets and I can't see if anyone else is on the sheet with me. And it's kind of important. I'm looking at financial statements with my director of finance, and I'm like, "Are you there? What page are you on?" And usually you can click on their avatar and go to where they're. And I start to Google, and it ends up being a tiny little arrow that is either pointed up or pointed down, and I'm like researching. I'm asking one of my office people, "Have you ever had this happen?" I turn my computer. The low level things, I think for many of us can be very frustrating.
Oh, absolutely. And certainly, so this is, user interface issues and so forth. There's a wonderful book I will recommend called The Design of Everyday Things by Donald Norman. I don't know if you've ever read this.
No, I'm going to put it in our chat.
No, this is a wonderful thing, and it's pretty old now, but it's still highly, highly, highly relevant.
So, again?
Donald Norman.
Okay.
And he was at Apple for many years. I don't know whether he's still there. The central one of the central ideas he gets across is if you want to control something, say Google Sheets, but this was written 30 years ago, there wasn't any Google Sheets. He was talking about really basic things like a refrigerator. Have you ever tried to adjust the temperature on your refrigerator? What are the controls? Well, there are two dials inside with numbers on them, but the dials tend not to be labeled. and they also don't do what you think. You think, oh, one of them is the temperature for the refrigerator, and the other one is the temperature for the freezer. No, that's not how it works. One of them is fan magnitude, and the other is controls how much of the cold air gets blown into the freezer versus into the refrigerator.
Hmm.
And it's horrible, right? It's very difficult, and basically you just sort of hope for the best. It's also really awful because it's difficult to get a feedback loop where you adjust one of these things and then you observe what happens, because it takes hours, and who has thermometers and stuff like that. Anyway, the central point that Donald Norman makes is that if you want to control something, you need to have you're going to create a model in your mind about how this thing works.
Mm-hmm.
And part of the job is for the object itself to present a relatively simple model of how it works. What I just described with the refrigerator, that's a horrible model, right? It's very difficult to control. It's not explained anywhere. It's sort of, hope that it works and all the rest of it. Complete failure.
And in my case, I have to stick a quarter into the radial dial to move it from position 1, 2, 3.
Because they don't want you messing with it, because you're just going to make it wrong, right? I mean, it's an absolute classic. I think the book has a number of these things. This is the one that sticks out in my mind. The direction I'm going with this, and this is sort of back to the technology is everywhere in our lives. We do need to interact with it. We do need to control it. One of the things you need are good models for how they work, and what they're able to do and what they're not able to do, and what they're able to figure out, and all the rest of that. And so where's the button on Google Sheets that controls the sharing? I mean, this is an extreme example of Sheets that shouldn't be quite so hidden.
Right.
But think about, you had to figure out a model of how this thing would operate, and what it can do and what it can't do, and what it can figure out, and so forth, to be even able to ask the question, why isn't it doing the thing that it needed to?
Right.
And this is ubiquitous. I helped my 80-year-old parents with a smart TV. I went back and visited them recently, and it was almost tolerable. They were able to find most of the passwords for most of the streaming services that they had subscribed to. This was the challenging thing. But oh my gosh, the number of, we can do this, but we can't do this one because it's not this model, and this is the wrong thing. So you need that kind of knowledge of how bits and pieces of technology might interact to navigate the world. And so to tie all this back, understanding what you can and can't do in Minecraft, and understanding how you connect stuff together in Legos and get the arms moving back and forth. All of that is about building models, both literally and figuratively, but then
Right.
about understanding what you can and can't do there.
Right. And I think it's also, in my situation, I'm not a computer scientist, but I've been around all of this for a long time, and I know a lot of the basics. For me, it was another lesson, and I think a lot about user interface. And in this case, I think we all have expectations that, in a way, we have to lower, that these things are going to happen to us many more times than 20 years ago. Where we just have so many interactions, and that if we can learn to have a lower fuse and learn to understand the number of questions to ask, and I think learning to program really helps with that.
Mm-hmm.
So it's not a disaster that I lost my ability to see other people, and it's just a process I'm going to go through.
Yeah, it's a different set of challenges of how to deal with things, right? Some people find computers incredibly frustrating. What I love about them is they're usually very, very predictable, right? If something goes wrong, it's going to go wrong again in the same way, in a predictable way. Now, that's not always true, and that's a whole nother story. But this is dramatically different than, trying to guess, if I meet somebody on the street and say something, what's the reaction going to be? Are they going to be friendly? Are they going to shoot me? It can really be all over the place, depending on where you are in the world and so forth. But it's a very different way of thinking because it has this reproducibility, but at the same time, no common sense, right? The trick with the computers is exactly, if you want to make a peanut butter and jelly sandwich, at the end of the day, all you're going to be doing is sending pulses out to motors.
Right.
And it's scary and interesting stuff. And to know that there is that world and it makes sense, but it's also phenomenally difficult. I think that's part of it.
So, Steve, tell me your favorite story of teaching somebody about programming, or one of them.
Ooh. There's been so many cases of that.
Well, while you're thinking, I'm going to tell you two that just always come to mind. And one is when I was a full-time computer teacher, I think I was teaching fifth graders, and I'd bring the kids together. We'd have a meeting, we'd talk, and then they'd go off and work on things. And then I'd bring them back together partway through, how's everyone doing? And one kid turned to me and said, Miss Hart, there's absolutely no way I can come to a meeting right now. I'm just too busy working. And I was like, oh, that's wonderful. A, wonderful that he feels like he can be that communicative, and B, that he's that involved in learning.
That is wonderful. Something I like to quote in the compilers class I teach, not only am I teaching these students a whole body of how to craft very high level, very complicated computer programs, but I force them to do it in a programming language that they've almost certainly never used before, that requires a different way of thinking and all the rest of it. And they just, grumble endlessly for the first month of the semester. The second half, they sort of begin to begrudgingly understand why they're doing that, and usually by the third month, when the home stretch or whatever, they get it. And one of the quotes I like to use, the student was complaining about the program that he wrote, and he was saying, never have I spent so much time to write so little code that does so much. Yeah. And the great thing is, I have no idea whether he was complaining or not, right? This is, to me, this is exactly it. You're solving this puzzle where you're trying to make this thing happen, and you do. It's very, very difficult. And the answer at the end of the day is this tiny little, oh, yeah, you just type that and it works.
Right.
But
I think it pushes a lot of different, one of the things that I noticed when I started teaching is how quickly kids would say, oh, that didn't work. I'm going to try something else. I'm going to try something else. And how I sometimes had to slow them down and say, don't change everything. Just change one thing. Because if you you won't know what made it work. But what was so clear to me was that as adults, we're like, oh, I made a mistake. It didn't work. Kids don't go through the I made a mistake. They just, oh, it didn't do what I wanted it to do. And they save a lot of emotional energy by, okay, that didn't, I'm going to keep going. Which is a nice help.
Maybe that's another whole pillar of why we should be teaching this stuff, and it's problem solving in general.
Yeah,
So I'm going to counter a little bit and say, it didn't work, try again. You want some of that, but you also want a little bit of intelligence in it, right? One of my favorite things to quote is this scene. It's from this, it's like 1983 Weird Al Yankovic movie, UHF, which is interesting of itself. But the scene I like to quote is there are two people sitting at a park bench. One of them is a blind guy, and he has a Rubik's Cube in his hand, and the other one is a sighted guy. And it works. The blind guy twists the Rubik's Cube, hands it over to the sighted guy. The sighted guy looks at it and says, no, hands it back to the blind guy, twists it again, hands it over, and so forth. There's some merit in that approach, and certainly you shouldn't be so afraid of making mistakes that you can't perform experiments.
Right.
On the other hand, when I see students programming like that, where it doesn't work, poke it randomly, try again, sorry, no, we're trying to teach you to be a little bit more thoughtful in
Right. Sure.
what do you think is wrong? Let's chase it down a little bit.
Yeah.
So either extreme is an extreme and inappropriate, but where that lies between it, that is actually a learning experience, and to sort of sort all that out.
Yes.
So that's you raise a very good point, and part of it's just we teach largely different groups of students.
Yes, we do.
There are probably more parallels than there should be, but
right. I often found I had to slow them down. Like, okay, why didn't it? Let's slow down. Let's just look at these steps. But I had an interesting experience last night that relates to why it's important to teach these kinds of things to kids. I had some very new immigrants who are resettling from Ukraine over for dinner.
Oh my!
And their English is not there yet. And what was so clear to me, and I'm also at the same time trying to learn Spanish and realizing how humbling it is to learn a new language, and I was explaining that where I live is 2 blocks from the Hudson River, and we came to the word blocks. And blocks, and that's where the common sense comes in, and you have to back up. And I was like, okay, how do I explain this concept? And a lot of that comes into programming, and my colleague was like, why don't you use meters? How many meters from, how do you translate one thought to another way of saying something? So there's a lot of time in programming where you're translating the big thought to all the little steps.
Mm-hmm. Yeah. Well, that's getting back to our abstraction thing, right? We're New Yorkers. We think in terms of blocks and avenues and blocks and so forth. And you think about it. Okay, yeah, it's 2 blocks down. That's a very convenient abstraction because I actually don't know how many meters there are in a block because, of course, it varies depending on where you are in New York and so forth and so on. But that's similar sort of thing. But yes, absolutely. How do you describe that? It's sort of funny. Some students and I are there's a relatively new thing in computer science, which is mechanical proofs of things. And so if you think programming in Python or Java or something like that is challenging, this stuff is mind-blowingly challenging. This is working at a level of detail that mathematicians find too tedious. So really basic things like you have to teach it what a natural number is because it doesn't know what it is. And from there, you have to teach it the rules of natural numbers. It turns out that plus is just, whatever associative operator you could come up with or something like that. Incredibly low-level stuff.
And what is this field called?
Well, automated proof assistance or something like that, computer-aided proofs or something like that. I'm happy to share some of the stuff. It is remarkably mathematical, and the irony is that it makes the rest of computer science look sloppy by comparison, if you can conceive of such a thing. It's orders of magnitude more fussy than this stuff. On the other hand, it's one of these things. If you can manage to solve the problem, if you can manage to thread the needle, in a right triangle, a squared plus b squared equals c squared. And there's just no way you can be wrong about it. Whereas you can write programs that seem to mostly work, but there's this one little case you missed, right? With this stuff, there's no cases that you missed.
Interesting.
And so it's this abstraction level of detail continuum that we're dealing with that varies a lot. And so even within computer science, there are examples of this.
I think we're just about out of time, but that's a really great place to leave. I think it's abstraction and then all of the different ways of dividing it into little pieces. And
Right, right. Well, problem solving in general, and in fact, we were originally going to talk about algorithms as being sort of the central thing, but I'm now beginning to think from our discussion here, yeah, maybe that's actually just part of it. That
okay.
you know,
Well, I mean, Steve and I talk every 2 months, so maybe algorithms is our next conversation because I think it's a term that's thrown around and most people don't really know what it is and what it means. And so I think that might be a fun one.
yeah, yeah, oh, absolutely, and I think it's one of these cases where you can find uh, instances of where you're doing algorithmic things in your life without sort of realizing that they are.
Exactly. Yeah.
And
Yeah.
if you knew that it was, hey, it makes more sense.
Yeah. Well, thank you again.
This
Um,
has been a joy as always. I'm glad we're
oh,
able to
you're
keep
so
doing
sweet.
this.
So for our audience, just to remind you, Stephen teaches computer science at Columbia, tenured professor. I'm Laura Hart. I have found a company called RoboFun. We're 24 years old, and we're offering on 102nd Street and Broadway lots of really creative, fun ways for your kids to learn using a lot of Lego robotics, not exclusively a lot of robotics, a lot of coding, both in the language called Scratch and also in Python. We work with 3 to 13-year-olds, and we are at robofun.org. And we're going to call it. Have a great day. Stay cool.
Yep, very good. Yeah, my uh, external thermometer seems to have pooped out, so it makes me wonder at this point.
I've noticed it with my iPhone. I cannot leave it outside in the sun.
Oh yeah, yeah, no, absolutely.
All right. Have a
Very, yeah,
wonderful day, and
okay.
we'll be in touch. Thank you
Yeah,
so
very
much.
good. Yep. Mm-hmm.